In this video, we're going to be doing an FRQ for work, energy, and power, and we have a curved track that leads into a circular loop of radius r as shown in figure 1. A block of mass m is released from rest from a height h on the track. The block slides down the track and around the loop without losing contact with the track. All frictional forces are going to be negligible. So we're asked to draw the FBD right here. So this is going to be when the block is at point P, aka here at the upside down position, like this. So when you're upside down, you're always going to have a weight force on Earth at the center of mass anywhere you are, regardless if you're upside down or not. And you're going to have upwards normal force. Actually, this is a huge mistake. Do not do that. That is actually going to be downwards because it's going to be perpendicular from the point of contact. So you can imagine at this instantaneous point, this is going to be your ground, right? And if you just look upside down or just think about it, it is always going to be perpendicular from the point of contact. It doesn't matter if the point of contact is upside down. It still has to be 90 degrees from it. And the only way for that to be so is for it to be pointing straight down. So it's going to be straight down. So don't get tricked by that. You have a normal force downward, and you have a FG, aka weight force, downward as well. So these are both going to point towards the center of the loop, and we can see that there is going to be no friction. Now we want to derive, in our next question, an expression for the speed of the block at point P. So how can we do this? We can use conservation of energy. Let's look at our problem. Well, when you are at your initial state, this is going to be when you're released from height h, right? So then your initial, up here, let's find all of our energy. So we have kinetic energy and we have gravitational potential energy. Here, kinetic energy will equal to 0. We'll just have UG. And our energy total is just composed of UG at this moment. However, when we're at point P, right, our energy is going to be equal to kinetic energy plus UG. Now let's think about what do we have here. So kinetic energy here is going to be 1/2 mv, and let's call this point P, velocity at point P squared, and we're going to have potential energy again. So that's going to be, let's call this mg times 2r, because this is twice the radius. We're using radius to define our height here. Now we can use conservation of energy. That states that initial is equal to final, right? Zero. And then so then you can multiply this. Awesome. So we have m cancels out from each term, right? So actually, what we can do before that, let's subtract 2mgr from both sides so we can factor. So now we're going to have to multiply both sides by 2 as well. So this makes sense because our block is going to start with our UG, gravitational potential energy, at the top of the loop. And when we're at the top of the loop, some of that energy is going to go back to our gravitational potential energy, while the rest is going to become kinetic energy. Now, for part 3, we want to derive an expression for the force exerted by the track on the block as the block passes through point P as a function of the initial height of the block. So we're going to do this by first looking at point P. Our inward direction is going to be downward towards the center of the loop. So we are going to think about when we have Newton's second law, this is radial, this is circular motion, and that is going to be when you have summation of the forces, that is mvp squared over r. In this case, we have vp for the p that we have here, point P. And since we know that both of them are going to be inward at the top, we can say that our acceleration, we can just make positive in this direction. Therefore, we're making those things positive. We have n plus mg, your weight, mg being weight, right? And then that's going to be mvp squared over r, right? So then we want to solve for n, and we get mvp squared over r minus mg. And we can also substitute in our velocity that we found over here, right? So we have vp squared definition over here. We'll take this and pull this up here as well. So we have this for vp. Now you're going to have n is equal to m2gh minus 2r divided by r minus mg. N is equal to mg 2h minus 2r divided by r minus 1. Now after this, keep simplifying this. Same thing. Just factor out that r. Now that's our normal force expression. If the frictional forces between the block and the track were not negligible, indicate which of the following changes could be made to the track to allow the block to still pass through point P without losing contact with the track. Well, if we have right now the current condition for contact with point P is going to be that your normal force exists and it's greater than 0. Now, if you have FK, friction present, it's going to make your mechanical energy degrade into a thermal energy unusable. So that means that V at point P will decrease. So to keep point P without losing contact, the block needs more E or easier contact solution condition. So it's going to lower point B.